Thanks for kind introduction, and I'd like to thank the organizers for giving me this great opportunity to present our recent results, and also for allowing me to join the conference remotely. So in this talk, I'd like to talk about the theoretical formulation to analyze the cavity QED in nonperturbative regimes, and also its application to the old problem, which is the dissipative quantum phase transition in Josephson junction. So this talk is based on these references. So first, I'd like to start from a general introduction about the physics of light matter interaction. So probably the simplest way for studying light matter interaction is to think about using a classical light, like a laser, a coherent laser, to manipulate some small quantum system like a qubit. And of course, there are many interesting developments, mainly in the context of laser physics in this respect. And another way is to use rather quantized electromagnetic field to manipulate a small quantum system. This field is often called cavity QED. So the basic idea is to confine the quantum electromagnetic environment into a small box, which is called cavity. And this tight confinement allows us to achieve the enhanced quantum light matter interaction. And we can achieve the strong coupling even in the absence of external driving. So this is because we can use the vacuum fluctuations of quantum electromagnetic field in the cavity here. And naturally, we can consider the many body counterparts of these studies. So namely, for example, we can consider using the classical light as a tool to periodically drive many body system. And this line of studies date back to the earlier work by Elias Park, and there have been many interesting developments in the context of rocket engineering. So the common difficulty in this field is that if we keep driving a many body system, there is an inevitable heating, and the system typically ends up with the infinite temperature state, which is usually not so interesting. And recently, as a possible way to avoid this type of problems, there's a recent emerging field, which is often called cavity QED materials. So the basic idea is to, instead of some small quantum system, so here people consider confining many body system like 2D material into the cavity, and using the cavity confinements to achieve the strong light matter coupling. And indeed, there have been many developments to achieve the strong coupling in many body regimes. So, for example, in the field of 2D material, the possibilities of enhancing the superconductivity or ferroctivity have been studied both theoretically and experimentally. And there's also an interesting recent experiment on demonstrating the non-trivial cavity confinement effect on quantum Hall transport. And also there are interesting developments in the field, which is called proprietary chemistry. Despite these recent interesting developments, so still the comprehensive description of this type of cavity QED material is lacking. So, for example, the basic question, like how to construct a faithful tight binding model at strong coupling, is still an open question. So, the main goal of the first part of this talk is to address this type of questions. And this part has been done in collaboration with Eugene Demla and Adachi Imamoru from ETH, and also with Takeru Yokota from RIKEN. And in the second part, I will talk about its application to the old problem of dissipative quantum phase transition in Josephson junctions. And this has been done with Kanta Masaki and Hiroki Tsudo, who are graduate students in the University of Tokyo, and also with Masaki Oshikawa from ISSP. So as I mentioned, the recent experiments are now achieving the stronger light matter interaction, and because these are the unprecedentedly strong interactions, they naturally lead to the new theoretical challenges because of the breakdown of conventional descriptions. And I'd like to illustrate such breakdown by considering a very simple example in cavity QED. So here we consider a single electric dipole coupled to a single cavity mode. And for simplicity, here I just model the electric dipole as a quantum particle trapped in effective double wave potential. So our starting point is this type of cavity QED Hamiltonian in the Coulomb gauge. And just for convenience, we can use the Bogoliubov transformation to derive the photonic bosonic operators here. And the common simplification for this type of model is to perform the two-level approximation, which is a projection onto the two lowest energy levels here. So by this projection, we can construct the model, which is called the quantum Rabi model. So basically this first term corresponds to this emitter energy, and this term corresponds to this light matter interaction, and this is just a photon energy here. But so this type of two-level approximation can easily break down at the ultra-strong coupling, which is now becoming possible in experiment. So here I plotted the excitation spectra at different light matter coupling strengths, and these green dotted curves correspond to the exact result of the original Hamiltonian, and these red curves correspond to the excitation spectra obtained from the quantum Rabi model after the two-level approximation. And we can see that these results start to deviate around the ultra-strong coupling regimes. And technically, this originates from the presence of large matrix elements in the P.A light matter interaction term. And physically, this originates from the strong light matter entanglement, but we will revisit this point later. So anyway, this demonstrates that we indeed need a faithful theoretical description beyond standard approximations in nonperturbative regimes. So we just saw that using the very simple model of cavity QED, so this type of projection onto the low energy manifold, so this type of approximation can in general break down at ultra-strong coupling in the Coulomb gauge. And now we are interested in the simplest example of cavity QED materials, which is a single electron trapped in periodic potential. And again, so a common simplification for this type of model is to consider the projection onto the lowest energy band, which is basically the tight bind approximation. But we know that from experience in cavity QED, so this type of projection on the low energy manifold can easily break down at strong coupling. So we here again may expect that this type of tight bind approximation can also break down at strong couplings in the Coulomb gauge. The answer is indeed yes. So here I plotted the energy band at different light matter coupling strengths. And these red dashed curves correspond to the results obtained from the tight bind model constructed in the this Coulomb gauge. And we can see that they dramatically fail in the sense that they neither capture the band flattening nor the level softening features here. So this motivates us to ask the question about how we can construct a more faithful tight binding description of this cavity QED material, which is hopefully valid at the arbitrary coupling strength. And our main idea is to introduce a new unitary transformation for this. So in the original Coulomb gauge, the strong light matter interaction naturally leads to the strong entanglement between these two degrees of freedom. But we constructed a unitary transformation by which we can transform to the flame where light and matter can be asymptotically decoupled. So this is a concrete expression for this unitary transformation. And for the sake of convenience, I switch to the second quantized notation here. But anyway, so we start from the QED Hamiltonian in the Coulomb gauge here. And this is an expression which can be obtained after applying this unitary transformation. And now the point is that, so in the original Coulomb gauge, this represents the light matter interaction, and G characterizes the bare coupling strength. And strong G naturally leads to the strong light matter entanglement due to this coupling. But after the transformation, this light matter coupling is absorbed as the shift of the electron coordinate here. And now the essential point is that, so in the transformed flame, the effective strength of this light matter coupling is characterized by this parameter Z. And this Z actually depends on the bare coupling strength G non-monotonically here. And in particular, this Z can go to 0 in the strong coupling limit. So in this sense, in this transformed flame, light and matter can be asymptotically decoupled. And so we can use this transformation to construct the tight binding model. And so here, these black dotted curves correspond to the result obtained from the tight binding model in the transformed flame. And we can see that they correctly capture the band flattening and level softening features, and also they provide asymptotically exact results in the strong coupling limit as expected. And so we can also apply it to analyze the Bailey phase and topology of cavity QED materials. So these results make a contrast with the results in the Coulomb gauge, where the description fails due to the strong light matter entanglement, which invalidates the level truncations in this plane. Okay, so so far we consider the rather simple case of single electromagnetic mode, but we can extend the whole theoretical formalism to the case of multiple electromagnetic modes. And now I like to talk about the application of this theoretical framework to the problem of dissipative quantum phase transition in resistively shunted Josephson junctions. So as you may know, this resistively shunted Josephson junction is a problem in which there is an artificial atom coupled to the quantum resistance. This is an iconic model to study quantum dissipation, originally suggested by Caldera and Leggett. And theoretically, we can analyze this system by using this equivalent circuit diagram. So there is an artificial atom of the Josephson junction, which is coupled to the long high impedance waveguide here. And microscopically, we can model this system by using the following Hamiltonian. And this is precisely the same form as we consider in the context of cavity or waveguide QED in the previous slide. So I shall say this Hamiltonian as the Coulomb gauge Hamiltonian. And now these phi and n are the Josephson junction phase and charging operators, which basically play the role of position and momentum operators in the previous slide. And this part is the microwave photon environment, and this NR is the vector potential degrees of freedom of this environment. And now the light matter interaction is described by this term, and its coupling strength is characterized by the this dimensional parameter alpha. And this alpha is defined by the ratio between the quantum resistance and the impedance of the waveguide R. And now this part environment is characterized by the frequency cutoff W. And importantly, we are here interested in the so-called wideband condition, meaning that this charging energy and Josephson energy are much less than the this frequency cutoff in the environment, because this is the situation which is typically realized in the actual experiments. And now, despite the simplicity of this model, for some reason there's a long-standing controversy regarding the quantum phase transition. So on the one hand, the perturbative RG analysis clearly suggests the presence of quantum phase transition at the alpha is equal to 1. But on the other hand, there's so far no concrete experimental evidence for this quantum phase transition. So we re-examined this problem by using the nonperturbative analysis. So our starting point is this Coulomb gauge Hamiltonian. And as I explained in the previous slides, so in this Coulomb gauge, the level truncation procedures which are necessary in NRG, so this can't be justified due to the strong light matter entanglement. So to apply the Wilson numerical renormalization group to the present problem, we use the again this unitary transformation, and using this we can decouple the Josephson junction degrees of freedom. And now the model looks like this. So this HTLL term describes basically the usual homonagala-Tinge-Liquid Hamiltonian here. And this part is the interaction term, and this contains the envelope function f nu here. And this f nu is characterized by the length scale nu, which is defined by the ratio between the frequency cutoff W and charging energy EC. And so far, all the things are just exact, so there's no ambiguity. But now, so the previous or conventional understanding goes as follows. So there's some simplification. So if we do the scaling dimensional analysis for this field theory, we can see that this variable nu is irrelevant in RG sense. So previously, people just assume the validity of taking this variable nu to 0. And in this limit, this envelope function f nu becomes just a Dirac delta function. So we can simplify this original Hamiltonian to this simplified model, which is called the boundary sign Gordon model. And there are many well-established methods to analyze the ground state of this boundary sign Gordon model. And it is very well established that its ground state phase diagram looks like this. So so if the coupling strength alpha is less than 1, this Josephson energy EJ is irrelevant. So the potential goes down, phase is delocalized, so the system is in insulator phase. And on the other hand, if alpha is larger than 1, Josephson energy is relevant. So the potential goes up, so the phase is localized and the system is in superconducting phase. Okay, so far so good. But there's one subtlety in this previous argument. That is, so if we consider the wideband condition, meaning that charging energy is much less than the frequency cutoff. So actually, this variable nu is much larger than 1. So this means that nu is actually a very large value at the initial stage of RG flow, or in another word, at a UV scale in the RG procedure. So it is not obvious. So this non-perturbative term can be just taken to be 0. And so we consistently include this nonperturbable term in the analysis. And surprisingly, we found that the results can qualitatively change due to this nonperturbative effect of large U. And in particular, this insulator phase is actually strongly suppressed because of the nonperturbative effect of this new term. And let me explain more about this. So to do this, we consider the DC phase mobility, which is basically an order parameter of this transition. If it is non-zero, this system is in phase localized insulator phase, and if it vanishes, the system is in superconducting phase. And here is our energy result, and so we can see that the values of this phase mobility initially grow. So in this sense, insulator phase is initially favored. And at small EJ over EC here, which correspond to these blue curves. So in these cases, there's an RG flow to the insulator fixed point with non-zero phase mobility. But at larger EJ over EC, so it changes from increasing to decreasing, and it eventually converges to the value of 0. So there is indeed a non-monotonic RG flow to the superconducting fixed point at larger EJ over EC. And we check this behavior by using an independent functional RG analysis, which is another non-perturbative RG method. And we basically confirm that qualitatively the same features as found in energy analysis. So, so at the initial RG flows, we see we can conclude that the EJ over EC decreases, and this is consistent with the fact that insulator phase is initially favored. And at small EJ over EC corresponding to these blue curves, so we indeed see the RG flow to the insulator fixed point here. And at larger EJ over EC, which are represented by these red curves, so these clearly show the non-monotonic RG flows here to the superconducting fixed point. So, so basically, both of this NRG and FRG analysis show that this variable U here is actually dangerously irrelevant in the sense that it is irrelevant in perturbative regimes, but it can be relevant in non-perturbative regime. So to relate our consideration to actual experiment, here we consider the phase coherence, which can be measured by the admittance at low frequency. And so this is basically another order parameter. So if it is non-zero, the system is in superconducting phase, and if it vanishes, the system is basically in insulating phase. And here I show the result of energy flow of this phase coherence. And looking at this, we notice that so to observe the quantum phase transition, we actually need a rather large number of RG steps here. So this means that we need to go deep infrared regime. And because infrared cutoff frequency is determined by either the lowest frequency of waveguide or final temperature. So this means that if we want to observe the signature of insulating phase with a vanishing phase coherence, we need to achieve the sufficiently low temperature and also sufficiently long waveguide length to achieve this low infrared cutoff frequency. And as one possible example, we propose to use a recently realized long high impedance superconducting waveguide which consists of a very large array of more than 30,000 Josephson junctions. And with this very long waveguide can achieve the very small infrared cutoff frequency. So this should be promising to observe the tendency to initiate a phase, which is basically the suppressed phase coherence factor. And we propose that this could be within the reach of recent experiment parameters. Okay, so I hope I convinced you that we introduced the new unitary transformation to analyze quantum light matter interaction. And we successfully constructed a faithful tight binding model for cavity QED materials. And in the second part, we extend the formalism to the multi-mode electromagnetic modes, and we revisited the old problem of dissipative quantum phase transition in Josephson junction. And we performed the nonperturbative RG analysis, NRG and FRG, and both analysis suggest that the transition should be possible, but only in this very restricted regime. So thank you for attention.
Look, okay, we have a question from the back, and then also from the front. Okay.
I'm a little bit confused. You consider transition from between insulator and superconducting states, and both of them are not dissipative. And still you call this transition dissipative. Is it just not very good terminology, or there is something more that you have in mind?
Okay, so my use of term dissipation means that there's a single Josephson junction which can be either superconducting state or insulating state, and this Josephson junction is coupled to the resistance, and in this sense, this quantum resistance can cause the dissipation onto this single Josephson junction. And so,
is your system dissipative or it's not dissipative?
It's dissipative in the sense that this Josephson junction is coupled to the quantum resistance. And we call superconducting or insulating phase. So that just corresponds to the either the this phase localized or phase delocalized phase in this single Josephson junction, which is coupled to the dissipative environment.
But dissipation means that energy goes from your system to somewhere, and here I can see where you want to send your energy and where you take it from.
Oh no! So there's a coupling between this Josephson junction and this quantum resistance. So this quantum resistance is basically, this can be modeled by the collection of harmonic oscillators here. And this interact with the Josephson junction from this coupling. So this Josephson junction can exchange energy with this dissipative environment.
But in both insulating and superconducting state, it will not exchange energy. The resistance will be in its own state, and all current will go without, or voltage will go without any dissipation. Anyway, sorry for it's probably just terminology.
Yeah, I guess so. So yeah, hopefully, yeah. So this clarifies to some extent better. Okay, thank you.
Thank you. We have another question in the front.
Yeah, so thanks for a great talk. So I was a little bit confused about how good this strategy is. I understand that this is really great in the sense that for G equals to infinity, it just asymptotically becomes just a free system. But does this strategy work for arbitrary G, like in a weak coupling regime? Because it looks like the psi became very strong.
So yeah, that's actually a good point. So as I said, after the transformation, the coupling strength is solely characterized by this coupling Z. And so this strategy is good as long as Z is small. So this applies to either very weak coupling regimes here or very strong coupling regime. So in this strategy, the most challenging regime is around this so-called deep strong coupling regimes.
I see. I have a quick another question about the latter part where you did this RG by using this transformation. I thought so. I was a little bit confused why the previous people couldn't figure this out, in the sense that, like, your transition point, if I'm reading the parameters correctly, isn't the boundary that you observed still in, like, like EJ over EC, am I correct that that's relatively the photon material coupling strength? And it's G equals to 0.3 is not super large, so I would have thought that this truncation method, although I understand that will like violate some of the gauge invariance, it's not going to surprise me if the previous, even if this transformation, even without the transformation, they could figure this out. But is there any reason that people could not see this?
So I guess so the main I would say problem in the previous understanding that so people just merely assume the validity of taking this variable to 0. And that is because so if we naively believe the scaling analysis, so this new its scaling dimension just means that this is irrelevant. So just people just merely I guess believe that we can just take this to be 0 and we can just neglect this. And in that case, the system is just boundary triangle model, and so there is no ambiguity here, but there's ambiguity in this assumption. And I guess that's the point.
Okay, thank you very much.
Thank you very much. We move on to the next speaker. Thank you very much for your talk.